All right, everyone. So now we're going to be talking about the complex number system. And this should have popped up already in terms of like you wondering what happens. And what I mean by that is this. For example, when we sit back and we think about, well, what is the square root of 4? Okay. Well, we know this is equal to 2. Okay. And we also know something like the square root of 9. Well, that's going to equal 3. But the question becomes, what happens, or why can't we do this? Like, how come the square root of negative 4 is not negative 2 or something like that? In fact, even if you went to your calculator, all right, if we went to our calculator here and we went and we asked the calculator, what is the square root of negative 4? Okay. See if I can get this window up. There we go. What's the square root of negative 4? Even your calculator knows that it's not a real number. In other words, this error, it says non-real answer, meaning the value of this is not real. All right. And sometimes it's kind of hard for students to kind of like wrap their head around a little bit. So what we're really talking about here is this. The result for this problem on the right-hand side, when we say it's a non-real result, what we're saying is the number that it actually is cannot be plotted on a number line. Because remember, real numbers or any real number can be plotted on a number line. And we have all different sets of numbers. We have counting numbers and whole numbers and integers and rational numbers and irrational numbers. But the result of this is called a complex number. Okay? In fact, the answer is 2i. So the question becomes, where did this I thing come in? All right. Now the I is what we call the imaginary unit. It's a brand new numbering system that we're going to learn. So the imaginary unit, I, is the number whose square is negative 1. Now, what this statement here is really saying is, if you have I raised to the second power, that is equal to negative 1. Or another way to kind of look at this would be, well, if we took the square root of both sides, I equals the square root of negative 1. So when we look at the square root of negative 4, what we're really saying here is we have the square root of 4 times negative 1, okay? And when we apply our properties for radicals, we can separate them. And we know the square root of 4 is 2. And by definition, the square root of negative 1 is I. And that's how we start dealing with negatives underneath an even index radical. All right? So we got this whole brand new numbering system. It's kind of like the real numbering system is like doing math on Earth, and then complex numbers is like doing math on Mars. They're two completely different sets. So what I want to do here is I just want to do a couple more examples of simplifying complex radicals here. So we're just going to simplify the following. So we'll start off easy, like the square root of negative 36 is going to be 6i. And how do we view this? Once again, I'll just erase and do the work. Once again, what you want to do initially is to kind of separate these two things, 36 times negative 1. Then apply that product rule for radicals. Separate them. Square root of 36 is 6. Square root of negative 1 by definition is I. So you would get 6i. Okay? Let's do one more. One of my personal favorites would be the square root of negative 20. Once again, we break this down. Let's do we're going to do 20 times negative 1, which is the square root of 20 times the square root of negative 1. Now the square root of 20 is 2 square root of 5 with an I on the outside. And traditionally, we will write this as 2I square root of 5. And the reason why we do this is I don't want us to make the mistake that this square root only stops at the 5. It does not include the I. So you would kind of just like sneak it in there because it's all being multiplied. 2 times the square root of 5 times I. So just move it over there using the commutative property of multiplication and you'll be fine. Now, I have been saying this thing called complex number a lot. But what exactly is a complex number? Well, a complex number is made up of two parts. Okay? And it looks like this. A plus or minus bi. So, in other words, you can have a plus bi or a minus bi. But most importantly, oh, I'm moving too fast. A complex number. There we go. All right. So most importantly, the letter A represents the real part. And then the bi is the imaginary part. Okay? But no matter what, even if you write 2i, it's really 0 plus 2i. All right? There's always a real part and an imaginary part. It's just if it's 0, you really don't have to write 0 for the real part. Just like leave it like that, okay? So what we're going to do here is let's go ahead and let's simplify some complex numbers by adding or subtracting. All right. So first we have the square root of negative 12 plus the square root of negative 27. So off to the right, here's the way I look at this. As soon as I see these negatives underneath the radical, I already know I'm going to have an I out front. All right, so the question becomes off to the right, just what is the square root of 12? Well, that breaks down into square root of 4 times 3, which is equal to 2 square root of 3. So 2i square root of 3 plus the square root of 27 is 9 times 3, which is going to be 3 square root of 3. So this is going to be plus 3i square root of 3. And since you have i's and like radicals, you can combine these by saying 2i plus 3i is 5i square root of 3. So it's really just everything that you've done before in terms of combining like terms. It's just now you're dealing with complex numbers. Okay? Let's do another one here. How about the complex number 3 minus 2i plus the complex number negative 5 minus 4i? Well, you got to remember, in reality, there are ones out front of each one of these quantities here. So you would have to distribute. So we would get 3 minus 2i minus 5 minus 4i. And then we combine the real parts and the imaginary parts. So 3 minus 5 is negative 2. And negative 2i minus 4i is going to be minus 6i. And yes, we do write them in traditional fashion, which means the real part is first and then the complex part is second. All right? The only problems that you got to be just a little bit concerned with would be something like 2 plus 2i minus negative 1 plus 3i. And the reason, we have to distribute that negative sign first. So 2 plus 2i plus 1 minus 3i. So distribute the negative sign. And then you can go ahead and group your real parts and your imaginary parts. So this will be 2 plus 1 is 3. And then 2i minus 3i is negative I. All right, so adding, subtracting, straightforward. Multiplying, we got to be careful. We just got to pay attention. We just got to pay attention to the definition of what that imaginary unit is. Okay? So remember, and I'm going to scroll up here real quick. Remember, here's our definition. The imaginary unit I is the number whose square is -1, and we can define this two ways. I squared equals -1, or I equals the square root of -1. Okay? And the reason why I'm saying that is because when you go and you multiply, let's say, 2i times 4 minus 7i, we're going to distribute the 2i. So 2i times 4 is 8i, because you remember, 2 times I times 4. Order doesn't matter when you multiply, so 2 times 4 is 8i, minus, but here, you actually get 14i to the second power. All right? When the bases are the same, you add the exponents. Now, by definition, we know I squared is equal to -1. So we are going to replace I squared with -1. And then we're going to write this in proper form with the real part first, the imaginary part second. -14 times -1 is going to be +14 plus 8i. Okay? And that's how you do this. It's not, I mean, it's very straightforward. It's just you got to remember, like, what, now that we're dealing with this imaginary unit, you got to remember what the imaginary unit stands for. I, square root of -1, but we just leave it as I, keep it nice and neat. I squared equals -1. This also extends into multiplying like full complex numbers. For example, 3 plus 5i times 2 minus, we'll just say 2 minus I. So what we're going to do here is distribute. All right, so distribute the 3 first. 6 minus 3i. Now we're going to distribute the 5i. So we're going to get plus, what is that, 10i? So I'll put it directly underneath. And then 5i times -i is going to be -5i squared. Combine our like terms. 6 plus 7i minus 5i squared. And then go ahead and do your by definition, I to the second. By definition, I to the second is going to be -1. So then you get 6 plus 7i plus 5. And finally, grouping your real parts, 6 plus 5 is 11 plus 7i. So like I said, it's just a matter of just keeping it as clean as possible, remembering all your little definitions. My personal favorites are conjugate pairs. So remember, conjugate pairs have their binomials where they have the same components but opposite signs. Same thing applies to complex numbers. Let's do 7 plus 6i times 7 minus 6i. All right? Now, because these are conjugate pairs, you don't have to do all that distributing. All you have to do is 7 times 7, 49. 6i times -6i is minus 6i to the second. We know I to the second. Oh, it's not 6, it's 36. Sorry. We know I to the second is -1. So basically what we have here is 49 plus 36, which when you simplify that is going to be 85. So 7i plus, or 7 plus 6i times its conjugate, 7 minus 6i, is 85. It's a real number, which is what I think one of the cooler things of what happens with this. All right. Now, the difficulty comes into play when you start multiplying like radicals and stuff. All right. Because many of us forget, like, how do I want to say this? Yeah, many of us just forget like the order of operations. All right. Like, for example, all right, now this is huge. If I asked you let's even do a simpler one. Really prove a point here. If I asked you to multiply the square root of -2 times the square root of -2, all right? Some of us would look at this and say, okay, well, if we have the square root of -2 times the square root of -2, some of us may say, well, that's going to be the square root of 4, which equals 2. And the reason why you may think that, okay, is because when we apply that product rule for radicals, you would get -2 times -2 underneath the radical. Then we would multiply this -2 times -2, which is +4. And that's how, like I said, some of us would result with 2 as a final result. However, none of that is correct. And the reason for that is you got to remember your order of operations, okay? When we actually do this, the thing we got to remember are radicals are really fractional exponents, which means you got to do the exponents first. Therefore, when you take the square root of -2 times the square root of -2 and rewrite it as -2 to the 1/2 power, you got to multiply by adding the base, or because the bases are the same and you're multiplying, you got to add these exponents together first. You got to do the exponent thing first. 1/2 plus 1/2 is 2/2. And that is what the answer is. The answer is actually -2. Okay? Now, the other way to think about this, which I'm hoping this is the way that a lot of us do this, would be to recognize that as soon as you see this negative underneath the radicals, just write the I out front first. All right? Now you've taken care of that negative thing. And remember, all this is being multiplied. So it's I times the square root of 2 times I times the square root of 2. So multiply the imaginary parts, I to the seconds. Now we can multiply the radicands. 2 times 2 is 4. And this is how we get -1 times 2, which is still equal to -2. All right? So just be careful when you're going through this. You don't want to rush, okay? My humble opinion, like I said, as soon as you see these negatives underneath that radical, write an I out front and just rewrite the radical exactly how it looks. That way you take care of any type of order of operation thing that you forgot to do first, okay? Now we're going to move into what we call dividing complex numbers, okay? And dividing complex numbers is not difficult. We've already seen some of the things that we have to do here. It's just taking our time, understanding what we're doing and why we're doing it, okay? So the first thing we want to do is understand. Actually, we'll do the more complicated one first. Let's say we wanted to simplify 3 over 2 plus I, okay? In general, we never write complex numbers in our denominator, okay? And the reason for that is we like to write our complex numbers in its standard form, a plus or minus bi. So if I have 3 over 2 plus I, the question now becomes, well, how do I get that I out of my denominator? Okay? And this is going to work the same exact way as when you were talking about dividing radicals, where you don't like radicals in your denominator. That was, what section was it? 8.5? I think it was 8.5. So in order to get that radical out of the denominator, you would multiply by the conjugate. So for us, we are going to do the same exact thing. By multiplying by the conjugate, remember, you don't have to do all of the distribution if you recognize that you have its conjugate. So in our denominator, here's what's going to end up happening. We multiply 2 times 2, which is 4. I times negative I, which is negative I squared. Okay? In our numerator, we're going to distribute the 3 to give us 6 minus 3i. And here's what's lovely about this. If you look in that denominator, by definition, I squared is negative 1. So you end up getting 6 minus 3i over 4 plus 1, which is 5. And the proper way to write this would be 6 over 5 minus 3 over 5i. And there's our answer in what we call standard form. So like I said, it was just like, doing the rationalizing the denominator. It's just now we're just multiplying by the conjugate so that we do not have any i's in our denominator. All right, I'll do another one here for us. We'll do like a more slightly complicated one here. So how about negative 3 over negative 7 plus 2i? So once again, we don't want the I in our denominator. So we're going to multiply by the conjugate. Negative 7 minus 2i. Negative 7 minus 2i. In our denominator, which is probably most likely going to be the easiest one, negative 7 times negative 7 is positive 49. 2i times negative 2i is going to be negative 4i squared. Now distribute that negative 3 in your numerator. So negative 3 times negative 7 is positive 21. Negative 3 times negative 2i is going to be, it's going to be plus 6i. And now just go ahead and simplify your denominator. You got 49 minus 4. By definition, I squared is negative 1, which is going to give you 21 plus 6i over 49 plus 5, which is 21 plus 6i all over. 49 plus 5 is 54. And then from here, you're just going to have to simplify what you can. So, for example, in the numerator, we could factor out a 3. And in my denominator, 3 times, 3 times 18 is really 54. So we can simplify the 3's to give us 7 over 18 plus 2 over 18i, which could be simplified even further to 7 over 18 plus 1/9 I. And that would be your final answer. So the whole problem, once you knock out this conjugate business, I think the most difficult problem about this is just simplifying it. Just making sure you get it all the way down. I don't know how far down WebAssign would like you to simplify. Personally, I'd go as far as you can. All right? But they might be a little lenient. They might accept this as a final answer. All right? I guess my best suggestion would be try it. All right? They'll tell you if it's acceptable or not. Personally, I always simplify as much as possible. Okay? Now, finally, we're going to look at what I think, honestly, is like the easiest part. However, it could be the most difficult if you don't know this little trick I'm going to show you. And it's not even a trick. It's a pattern that ends up developing. All right? So we know I is equal to the square root of negative 1. And we also know I to the second equals negative 1. Now, if I kept doing this, like I to the third, well, I to the third would be nothing more than just I times I to the second. And we know I is the square root of negative 1. And then I to the second is negative 1. So this would just turn out to be negative square root of negative 1. Or, and the easiest way to say this would be negative I. All right? Because you have a negative out front, and by definition, the square root of negative 1 is I. Okay? I to the fourth is really I to the second times I to the second, which is negative 1, times negative 1, which equals positive 1. Now, if you follow this pattern here, I to the fifth, well, I to the fifth is I to the fourth times I to the first, which is 1 times I, or just simply I. I to the sixth equals I to the fourth times I to the second, which is 1 times negative 1, which is negative 1, sorry. I to the seventh equals I to the fourth times I to the third. But we know I to the third, upper right-hand corner of your screen, I to the third is negative I, so this would be 1 times negative I, which equals negative I. And then I to the eighth equals I to the fourth times I to the fourth, which is 1 times 1, which equals 1. Now, what I'm going to do is this. In the upper left-hand corner of your screen, I'm just going to erase the square root of negative 1 and just replace it with I equals I. And what you're going to notice here is this. You have I, negative 1, negative I, 1. Now, I, negative 1, negative I, 1. In other words, this pattern, I, negative 1, negative I, 1, will end up repeating itself over and over again. So, I equals I to the second equals negative 1, I to the third equals negative I to the fourth equals 1. I to the fifth equals I to the sixth equals negative 1, I to the seventh equals negative I to the eighth equals 1. And I'll do one more. I to the ninth equals I to the 10th equals negative 1, I to the 11th equals negative I, and then I to the 12th equals positive 1. And the key is right here at the very bottom. If your exponent is a factor of 4, or is a multiple of 4, then you will always get 1 as a result. So, I to the 16th equals 1. I to the 20th equals 1. I to the 24th equals 1. And so forth. Now, why is this important? Well, if I wanted you to simplify, let's say I to the 73rd power, all right, all you would have to do is this. Take 4 and divide it into 73. 4 goes into 7 once. 4 goes into 33 8 times. And notice, whatever your remainder is, that's exactly what this is going to turn out to be. So you're going to look for the exponent where this is a 1, and that, and I'll highlight it for you in green, is going to be right here. Because there's your exponent of a 1. So I to the 73rd power equals I. Now, how about I to the, let's do 85th power. Okay? Once again, take 4, divide it into 85. So 4 goes into 85. Or, I'm sorry, 4 goes into 8 twice. Drop down to 5. 4 goes into 5 once. So once again, you get a remainder of 1. So I to the 85th is equal to I. All right. And let's do one more just to show you. I to the 87th. Take 4, divide it into 87. 4 goes into 8 twice. Drop down the 7. 4 goes into 7 once. With the remainder of 3. So I to the 87th power equals I to the 3rd, which is really just negative I. All right. So I know it seemed like a lot of work trying to figure out these patterns, but once you know the pattern, it's very simple. Okay. And that's going to be it for this lesson. We are really going to start seeing complex numbers in the next chapter when we start solving quadratic equations. Now, you've solved quadratic equations before in the past. However, you solve them by only factoring. The question becomes, what if it can't be factored? Then what do you do? So we'll worry about that in the next video. But other than that, I will talk to you soon. Bye.